Hour 12. Economic meltdown. Stock exchanges have already shut down. Banks freeze digital accounts. With ATMs offline and card readers dead, cash is king again, but very few people have any. In cities, food deliveries stop. Public transportation collapses. Confusion turns into panic buying. Social media blackouts spread rumors faster than truth. Emergency services become overwhelmed, not just by crisis response, but by failing communication links. Day 2. Supply chains collapse. Global shipping fleets, now lacking reliable GPS, drop anchor. Air travel is grounded indefinitely. Fresh food disappears from shelves. Hospitals run out of fuel. Some cities go dark entirely. Week 1. Lawlessness. With no communications, no access to money, and basic services failing, law enforcement struggles. Looting, fires, and street-level violence break out. Governments deploy troops to maintain order. But coordination is slow and fragmented. Some people turn to radio for information. Others form community patrols. Society begins to restructure locally. Months later, certain countries restore limited power, prioritizing critical services, but others remain dark. Some transformers take years to replace. The death toll, mostly from heat, cold, disease, and lack of access to medicine, climbs quietly. And above it all, the sun keeps shining, calm and indifferent. This isn't a movie script. It's a plausible scenario, acknowledged by NASA, NOAA, and multiple governments worldwide. At Infinity Beyond, we aren't trying to sound alarms. We're sounding the truth. We live in a civilization built on fragile technology, dependent on systems we don't see, and vulnerable to a star we can't control. And the more we know about that star, the better chance we have to survive its storms. In the next segment, we'll explore what steps individuals and communities can take today to prepare for solar emergencies. From backup power to communications alternatives, we'll lay out a realistic plan to protect your family, your home, and your future. Because if this worst-case scenario ever comes true, preparedness could mean the difference between order and collapse. So what can you do? How do individuals and communities prepare for a disaster that comes without sound, without warning, and travels at the speed of light? At Infinity Beyond, we believe preparedness is no longer optional. You don't need to be a survivalist. You just need to be smart. Here's a practical step-by-step guide for preparing yourself and your family for a solar storm scenario. Solar-powered chargers, hand-crank radios, and battery banks are essential. Your smartphone is useless without electricity, so keep a solar or crank backup in your emergency kit. Consider investing in a portable solar panel system that can recharge small devices or LED lights. Print out or download key documents: ID, insurance, emergency contacts, medical info. Store them in a waterproof bag or USB drive with your emergency kit. Cloud backups won't help if the internet is gone. Stockpile at least 2 liters of water per person per day for a minimum of 7 days. Include non-perishable food, canned goods, protein bars, rice, dried fruits. Don't forget manual tools like a can opener. Purchase a battery-powered or hand-crank radio that can receive NOA or local emergency broadcasts. CB radios or walkie-talkies can be useful for local communication if cell towers fail. Establish a family contact plan with an agreed-upon meeting location and emergency contact person outside your region. Consider a home generator or at least a backup power station for essential medical devices. Surge protectors and manual disconnects can help prevent appliance damage during power surges. If you live in an apartment, keep a go bag ready with basics in case you must evacuate. In prolonged blackouts, social unrest may become a concern. Ensure doors, windows, and valuables are secured. Consider learning basic first aid and self-defense, especially in urban environments. Bookmark NASA's Space Weather Prediction Center, SWPC, or apps like Aurora Alerts, which can provide real-time updates on solar activity. Join online communities or local emergency groups focused on disaster preparedness. You don't need to panic, you just need to plan. At Infinity Beyond, we believe the real power lies in resilience, not resistance. The sun is beyond our control, but our reaction to it isn't. By preparing today, you buy yourself time, safety, and clarity tomorrow. In the next segment, we'll explore how governments and global institutions are shaping coordinated responses to large-scale solar disasters and what it means for national security, economics, and the future of civilization. Because in the face of a solar storm, every second and every choice matters. At the government level, preparing for a catastrophic solar storm has evolved from being a niche scientific concern to a full-scale national security priority. Why? Because a single solar event could do more damage than any cyber attack, military strike, or natural disaster in modern history. At Infinity Beyond, we take you inside the growing global response and why politicians, scientists, and military leaders are finally taking space weather seriously. In the United States, the White House, Department of Homeland Security, DHS, and Department of Defense, DoD, have issued several national action plans to address space weather risks. In 2019, the National Space Weather Strategy and Action Plan was released, outlining objectives to improve forecasting through satellite investment, protect critical infrastructure like transformers and satellites, coordinate federal response protocols in the event of a major solar event. The Federal Energy Regulatory Commission, FERC, now requires utilities to harden their infrastructure against geomagnetic disturbances, including simulations and stress testing of power systems. The European Space Agency, ESA, is developing its Lagrange Space Weather Mission, which will sit at Lagrange Point 5 to provide advance warning of Earth-directed CMEs, potentially hours or days ahead of impact. Meanwhile, the UK's Met Office Space Weather Operations Centre and the German Aerospace Centre are conducting national grid vulnerability studies. In Sweden and Finland, both countries with high geomagnetic risk, governments are investing in modular transformers, hardened substations, and public resilience education. Japan, vulnerable both to solar storms and earthquakes, now integrates space weather data into its national disaster warning systems. China is building a network of space weather observatories linked to its satellite fleet and military assets. India has launched the Aditya L1 mission, its first space-based solar observatory to monitor the sun from the Lagrange point L1. These regional efforts reflect a growing consensus. The next global catastrophe may not come from Earth, but from the sun. International collaborations are also strengthening. NASA and ESA regularly share solar data. The International Space Environment Service, ISES, coordinates 18 space weather centers worldwide. There are even military-to-military briefings on solar risk as it pertains to satellite defense, missile guidance systems, and undersea communication cables. The United Nations has even discussed space weather at the level of disaster risk reduction, recognizing that a Carrington-class event could qualify as a global humanitarian crisis. At Infinity Beyond, we ask, will this preparation be enough? Some experts worry that planning is still too slow, too underfunded, and too reactive. Global power grids remain deeply interconnected and largely exposed. And supply chains for critical equipment, like high-voltage transformers and radiation-hardened chips, are still fragile. In our next segment, we'll examine the future of solar defense, how humanity might one day build spacecraft shields, magnetic deflectors, or even orbital solar observatories that guard the Earth like planetary armor. Because the more we depend on technology, the more we must defend it from the sky. What does the future of solar defense look like? At Infinity Beyond, we envision a world where Earth isn't just a passive target for solar storms, but a planet actively shielded by technology, prepared not only to predict solar threats, but to intercept, absorb, or even deflect them. Let's explore the emerging ideas that may one day form a protective barrier between us and the Sun. One concept under discussion is the use of space-based magnetic shields, giant satellites placed at Lagrange point L1, which could generate powerful magnetic fields or plasma bubbles to deflect or weaken solar particle streams. This would be the first artificial magnetosphere ever created, essentially an electromagnetic umbrella between the Sun and Earth. The idea sounds like science fiction, but some models suggest a plasma sail or magnetic loop system could redirect enough particles to significantly reduce CME damage, especially if deployed far from Earth to allow early deflection. Future satellites and power grid components may be built with radiation-hardened materials using nanotechnology. These materials would insulate critical systems from both high-energy proton bombardments and electromagnetic surges. NASA is already testing self-healing materials inspired by biology that can seal radiation-induced microfractures in spacecraft hulls. Think of it as smart skin for machines, capable of repairing itself after a solar hit. A fully integrated global system of low Earth orbit, LEO, and deep space solar observatories could form a real-time solar surveillance net. Each observatory would monitor solar flares, CMEs, and solar wind patterns with AI-assisted diagnostics, sending alerts to Earth in seconds. Imagine this as an orbital shield of eyes, constantly watching the Sun's every move, capable of triangulating the direction and intensity of any incoming solar storm. The goal? Global warning within 60 seconds. Building on models like Dagger, future AI systems could evolve into autonomous decision hubs, capable not only of predicting, but also of initiating automated defense responses. Power grid modulation, satellite orbital adjustments, drone rerouting, civil alert broadcasts. AI would serve as the brain of planetary defense, responding far faster than human analysts ever could. Following in the wake of the Parker Solar Probe and Solar Orbiter, next-generation missions may attempt to collect solar particles in real time, return them to Earth, and help scientists understand the precise behavior of solar magnetic fields at the source. This would be the equivalent of sampling the Sun's blood, giving us deeper insight into its cycles and its tempers. Some theorists propose building solar weather stations on the Moon, where observatories could operate without atmospheric interference. Others dream of an eventual lunar far-side shield, a base that could double as both a defense system and an early warning platform. At Infinity Beyond, we believe that space is no longer the final frontier. It is our newest battlefield, but not one of weapons or conquest. It is a battlefield of resilience, knowledge, and cooperation to protect Earth from a threat as old as light itself. In our next segment, we'll reflect on the spiritual and philosophical questions raised by our star. What does the Sun represent to humanity? A god, a giver of life, or a destroyer of civilizations? Because to understand the Sun is not just to understand the universe, it is to understand ourselves. As these magnetic fields become increasingly complex and tangled, they create immense pressure. Eventually, this magnetic energy can no longer be contained. When it's released, it launches a phenomenon known as a coronal mass ejection, CME, a vast cloud of charged particles and magnetic fields blasted into space. If Earth lies in the path of this CME, the result is a geomagnetic storm that can severely impact satellites, GPS systems, aviation, and even the power grid on the ground. At Infinity Beyond, we take a closer look at these invisible threats. The Earth's magnetic field, our first line of defense, usually absorbs or redirects most of the solar wind. But during strong solar events, even this protective shield can be compromised. These particles slam into the atmosphere, creating breathtaking auroras across the sky, yes, but also straining communication systems and sensitive electrical infrastructure. This interaction between solar wind and Earth's magnetosphere is known as space weather. On a normal day, space weather is mild. But during peaks in solar activity, such as during solar maximum, the frequency and intensity of flares and CMEs increase dramatically. We're entering just such a phase now, solar cycle 25, which is proving to be more active than initially predicted. Unlike hurricanes or earthquakes, solar storms offer almost no visible warning signs to the average person. There's no howling wind, no shaking ground, only invisible particles racing through space at thousands of kilometers per second, heading straight toward Earth. So, as we continue to rely more heavily on satellites, internet infrastructure, and global connectivity, we also become increasingly vulnerable to the sun's temperamental bursts. That's why understanding the mechanics of the sun's activity and learning how to predict and mitigate the risks is no longer a distant scientific curiosity. It's an urgent necessity. At Infinity Beyond, we aim to demystify this cosmic challenge. In the next chapter, we'll journey back to 1859 to explore the Carrington event, history's most powerful solar storm, and ask the question, what if it happened again today? The last time a truly powerful solar wind hurricane slammed into Earth was on September 1st, 1859, an event now famously known as the Carrington event. That day began like any other, but out on the surface of the sun, something enormous had started to brew. A towering arc of solar plasma surged upward, rapidly expanding and glowing with intensity. This explosion, many times the size of Earth, was no ordinary flare. It was a massive coronal mass ejection, CME, and it was pointed directly at our planet. Within just 18 hours, an astonishingly fast journey for solar particles traveling 150 million kilometers, the CME reached Earth, igniting a chain reaction never before witnessed in modern human history. The skies lit up with brilliant auroras, not just in the polar regions, but as far south as Cuba, Mexico, and even Jamaica. People in New York and Boston thought it was morning and rose early, confused by the eerie glow filling the night. For those living in the 19th century, this was both mesmerizing and terrifying. Imagine seeing the sky pulse in green, red, and purple bands, without having any scientific understanding of why it was happening. Many thought it was the end of the world, but the visual display was just the beginning. Back then, the most advanced technology was the telegraph, the backbone of long-distance communication. As the storm struck, telegraph wires across continents sparked and caught fire. Operators reported receiving electric shocks, some strong enough to knock people unconscious. Telegraph systems went haywire. Some continued operating even after being disconnected from their power sources, seemingly powered by the solar storm itself. Entire networks went down. Communication collapsed. And yet, this was 1859, a time before power grids, satellites, aviation, or internet systems. The technology was minimal, and even so, the disruption was severe. Today, a Carrington-level event would have catastrophic consequences. At Infinity Beyond, we often ask a simple question. What if this happened now? Consider this. Our world is completely dependent on electronic infrastructure. From mobile communication and GPS navigation to air traffic control and banking systems, everything is interlinked and vulnerable. A CME of similar intensity today would overload transformers, knock out satellites, fry GPS systems, and possibly cause a global blackout. Governments and space agencies like NASA are aware of this threat. In fact, they've classified space weather as one of the greatest risks to national infrastructure. But the truth is, the Earth has had close calls since 1859. In 1921, the Great Railroad Storm disrupted train networks. In 1989, a weaker CME blacked out the entire province of Quebec, Canada, in less than 90 seconds. And in 2012, a storm narrowly missed Earth by just 9 days, an event that could have caused trillions in damages if it had struck. These aren't science fiction scenarios. These are real events, documented and studied. The Carrington event was a wake-up call, a silent warning from our sun that despite its warm glow, it holds the power to erase centuries of human progress in a matter of hours. At Infinity Beyond, we dive deep into these forgotten cosmic warnings. And in the next segment, we'll revisit some of those near misses, especially the terrifying solar storm of July 23, 2012, when Earth dodged devastation by a mere twist of timing. Because the truth is unsettling. We're overdue. And next time, we might not be so lucky. July 23, 2012. While most of the world went about its day unaware, our solar system narrowly escaped what could have been a cataclysm. On this date, the Sun unleashed two massive coronal mass ejection, CMEs, enormous clouds of electrified plasma that tore through space at blistering speeds. Had Earth been in the line of fire just 9 days earlier, the result could have been devastating. According to NASA, it would have been the modern-day equivalent of the Carrington event, but with consequences on a global scale. At Infinity Beyond, we ask, what if we hadn't been lucky? The 2012 storm was composed of two CME waves that collided shortly after being ejected from the solar surface, creating a supercharged storm front. Traveling at more than 3,000 kilometers per second, it reached Earth's orbital path in under 19 hours. Thankfully, Earth had already moved ahead in its orbit, and the storm missed us by a cosmic sliver. But if that event had struck Earth directly, the aftermath would have been catastrophic. Satellites in orbit would have failed. GPS systems used for aviation, military targeting, navigation, and finance would have gone offline. Internet backbones, including underwater communication cables, would have been severely affected. Even in the ocean depths, the surge of electromagnetic radiation could corrupt fiber optic repeaters essential for transcontinental data transmission. Entire nations would have suffered a communication blackout. On land, electrical grids would have faced an assault of geomagnetically induced currents, DC currents surging through infrastructure designed only for AC. Transformers, the heart of power delivery, would overheat, melt, or explode. Recovery could take months, even years, as transformers are expensive and complex to replace. September 1, 1859. English astronomer Richard Carrington was observing the Sun when he witnessed two intense flashes of light erupt from its surface, what we now identify as a solar flare. Unbeknownst to him, these flashes marked the beginning of the most powerful solar storm in recorded history, the Carrington event. Within just 17.6 hours, the Associated Coronal Mass Ejection, CME, slammed into Earth's magnetic field, faster than almost any other CME ever observed. The results were immediate and astonishing. Night skies lit up in blood-red, green, and violet auroras, visible as far south as Cuba, Mexico, and even Colombia. People in the northeastern United States awoke thinking it was dawn, only to realize it was still the middle of the night. The skies were so bright that newspapers could be read outdoors without a candle. But what truly stunned the world was what happened next. At Infinity Beyond, we revisit this moment as the first time human technology met the fury of the sun. Across the globe, telegraph systems, the lifeline of 19th century communication, began to fail spectacularly. Sparks burst from telegraph machines. Operators were shocked. In some places, the lines caught fire. Despite being disconnected from any power source, the equipment continued transmitting signals, powered solely by induced geomagnetic currents created by the storm. Entire communication networks collapsed, and in many areas, repair efforts took weeks. The intensity of the currents overwhelmed copper wires, melted relay switches, and set telegraph offices ablaze. It was, quite literally, a fire from the sky. And all of this happened in a time before satellites, computers, or electrical grids. At Infinity Beyond, we ask the question, what if the Carrington event happened today? Unlike the 19th century, our society is no longer analog. We are digital, global, and interdependent. Nearly every aspect of modern life, from banking to hospitals to logistics, is run through vulnerable electronic systems. Imagine geomagnetic currents coursing through underground cables, overloading transformers, and melting power substations. Imagine satellites being knocked out of orbit or fed corrupted GPS signals, affecting air traffic and maritime navigation. Mobile towers fail. Emergency broadcasts vanish. Water systems, powered by electric pumps, stop working. Refrigeration fails in grocery stores. Hospitals lose backup power. And like the telegraph operators of 1859, we wouldn't even see it coming until the lights go out. Some scientists estimate that a modern-day Carrington-level event could cost the global economy over $2.6 trillion in the first year alone. Full recovery might take 5 to 10 years, especially for power grid infrastructures with long lead times on replacement transformers. Fortunately, awareness is growing. In the U.S., agencies like NOAA, NASA, and the USGS have established real-time monitoring systems. But early detection remains a challenge, especially for solar flares, which travel at the speed of light, reaching Earth in mere minutes. In our next segment, we'll explore how space agencies and governments are racing to build early warning systems, develop AI prediction models, and install protective infrastructure before the next big one strikes. Because if the Carrington event was our first warning, it might also be our last chance to listen. In the wake of near misses like the 2012 solar storm, and remembering catastrophic events like the Carrington event, governments and scientists around the globe have launched an urgent race, not to stop the sun, but to predict its temperamental eruptions before they reach us. At Infinity Beyond, we explore how space weather forecasting is becoming one of the most important and underappreciated scientific fields of our time. In the United States, the National Oceanic and Atmospheric Administration, NOAA, operates the Space Weather Prediction Center, SWPC, in Boulder, Colorado. This facility monitors solar activity 24/7 using ground-based magnetometers and a fleet of dedicated satellites, including SOHO, GOES, and the Solar Dynamics Observatory. When a solar flare or CME is detected, SWPC issues alerts to power companies, airlines, satellite operators, and even emergency services. Meanwhile, the U.S. Geological Survey, USGS, tracks geomagnetic field changes from 14 ground observatories. Together, these data points allow scientists to gauge not just whether a solar storm is coming, but also how strong it might be and which regions of Earth are likely to be affected. In the United Kingdom, solar storms are now included in the National Risk Register of Civil Emergencies. The UK's Met Office has established its own Space Weather Operations Centre, and the National Grid has begun installing new transformer designs that are more resilient to geomagnetically induced currents. During a major CME, the strategy would be to activate all 8,000 kilometers of UK power lines to evenly distribute incoming currents, reducing pressure on any one point in the system. But even with all these systems in place, there's still a problem: time. Solar flares, especially those classified as X-class, travel at the speed of light. By the time we see them, it's often too late to protect vulnerable systems. That's why AI is now being recruited to predict solar activity before it happens. Enter Dagger, the deep learning geomagnetic perturbation model, developed by NASA and university researchers. Dagger uses real-time data from spacecraft observing the solar wind and applies a deep learning algorithm, a type of artificial intelligence that learns patterns from past events to forecast future disturbances. What makes Dagger revolutionary is its speed and accuracy. It can issue predictions every 60 seconds and warn of geomagnetic impacts up to 30 minutes in advance globally. In tests using historical solar storms from August 2011 and March 2015, Dagger was able to precisely map the timing and geographic impact of the disturbances. At Infinity Beyond, we believe this is a game changer. Imagine a future where power stations receive automated alerts and shut down vulnerable sections of the grid just minutes before a CME arrives, where satellite fleets shift into safe mode with seconds to spare, where airlines reroute flights and astronauts retreat to shielded modules in orbit, all because a solar siren warned them in time. That future is beginning now. In our next segment, we'll follow the journey of the Parker Solar Probe, NASA's fastest spacecraft ever built, as it dives into the outer layers of the Sun itself, seeking answers at the source of the storm. Because to protect Earth, we must first understand our star. The Parker Solar Probe is humanity's most daring attempt yet to understand our star, not from afar, but by flying directly into its atmosphere. Launched in 2018, this NASA mission was designed to dive closer to the Sun than any spacecraft in history, traveling through the outer layer of the solar atmosphere known as the corona. At Infinity Beyond, we view this mission not just as a triumph of engineering, but as a desperate necessity in a world increasingly at risk from solar storms. Moving at speeds exceeding 690,000 kilometers per hour, or 430,000 miles per hour, the Parker Probe is the fastest human-made object ever built. Its trajectory will bring it within 6.2 million kilometers of the Sun's surface, 7 times closer than any previous mission. To survive this extreme environment, it's equipped with a carbon composite heat shield capable of withstanding temperatures over 1,370 degrees, 2,500 degrees. But what's more impressive than its speed or endurance is its mission objective: to touch the Sun and bring back answers. By flying through the corona, Parker is collecting data on solar wind, magnetic fields, plasma flows, and energetic particles, the very ingredients of the storms that threaten Earth. The corona is where CMEs and solar flares originate, but until now, it has remained one of the most mysterious regions of our solar system. Why is the corona hotter than the Sun's surface? How does solar wind accelerate to such high velocities? And most importantly, can we predict eruptions before they begin? Parker's onboard instruments, like the Field Suite, SWEEP, Solar Wind Electrons, Alphas and Protons, and WHISPER, Wide Field Imager, are gathering unprecedented insight into these phenomena. Already, Parker has made groundbreaking discoveries, such as detecting switchbacks, kinks in the magnetic field lines that could explain how energy escapes the Sun. As Comet K2 makes its way deeper into the inner solar system, the big question that astronomers are asking is, what's next? What will happen to this massive icy object as it draws nearer to the Sun? Will it continue to glow brilliantly, offering skywatchers a rare and beautiful sight? Or will it fragment, disintegrate, or even completely vanish, like so many other comets before it? The truth is, comets are notoriously unpredictable. Their behavior can change drastically, sometimes without warning. As they approach the Sun, increasing solar radiation can either fuel them into spectacular displays or tear them apart. The balance between these two outcomes is delicate, and we're not yet sure where K2 stands. According to the current trajectory and velocity calculations, Comet K2 will reach its perihelion its closest point to the Sun, on December 19, 2022. At that moment, it will be about 1.8 astronomical units, AU, from the Sun. That's roughly 270 million kilometers, still much farther than the Earth's own distance from the Sun. That's a key point. K2 is not expected to get close enough to the Sun to produce the kind of super bright display that other sun-grazer comets have in the past. But that doesn't mean it won't still be worth watching. From now through the end of 2022, the comet will remain visible with small to medium telescopes, particularly in the southern hemisphere after mid-September. As Earth's position changes relative to K2's path, our perspective improves, and observers from countries like Australia, Chile, South Africa, and Argentina will get the best views. This southern visibility window gives us a continued opportunity to study the comet in detail, especially with professional observatories. Astronomers will be monitoring its activity level, tail evolution, and coma structure, looking for signs of fragmentation or fading. Infrared telescopes, spectrometers, and even amateur astronomers will all play a role in this effort. But what if K2 breaks apart? It wouldn't be the first comet to do so. In fact, many comets don't survive their first close encounter with the Sun. The heat and gravitational forces can crack them, especially if their structure is weak or porous. In some cases, we've even witnessed comets split into multiple pieces, like Comet Ison in 2013 or Comet Shoemaker-Levy 9, which famously broke up before colliding with Jupiter. However, K2 has shown surprising resilience so far. The fact that it's already been active for years and has maintained a stable coma and tail suggests a certain structural strength. It's also approaching the Sun at a safer distance than many previous comets, which reduces the likelihood of total disintegration. That said, until it completes its perihelion, we can't be entirely certain. Another possibility? K2 could go dormant. As the comet rounds the Sun and begins to head back toward the outer solar system, its source of heat will fade. The outgassing will slow, the coma will dissipate, and the tail will vanish, leaving only a frozen, silent object drifting once more into the dark. Whatever the outcome, one thing is sure. We're watching a cosmic drama unfold in real time. From its ancient origins in the Oort Cloud to its long journey through the void, Comet K2 is a time capsule of the early solar system, telling us stories written in dust and ice. At Infinity Beyond, we encourage you to keep your telescopes pointed skyward and your curiosity alive. In the next and final segment, we'll reflect on what Comet K2 teaches us about the formation of our solar system and why events like this ignite wonder in the hearts of people across the planet. 5 years ago, in 2017, astronomers pointed the Hubble Space Telescope toward a seemingly empty region of space far beyond the outer edge of our solar system. What they found would soon astonish the world of astronomy: a massive, icy object silently drifting inward toward the Sun. This was no ordinary celestial body. It was an 18-kilometer-wide comet, designated C 2007 K2 PANSTARRS, or simply Comet K2. This marked one of the farthest active comets ever discovered. At the time of its detection, K2 was floating somewhere between the orbits of Saturn and Uranus, an astonishing 2.4 billion kilometers from the Sun. That's about 16 times farther than Earth's distance from the Sun. Even from that great distance, it was already active, spewing gas and dust, forming a visible coma or glowing envelope around its nucleus. Since that historic discovery, Comet K2 has been making its way steadily toward the inner solar system. Now, in July 2022, it's reaching a rare moment in its journey, the point of closest approach to Earth. On July 14, 2022, the comet came within 270 million kilometers, 168 million miles, of our planet. Although this may sound distant, in cosmic terms, It's a relatively close encounter, and an opportunity skywatchers have been anticipating for years. While Comet K2 may not become as visually spectacular as some famous past comets like Hale-Bopp in 1997, its uniqueness lies in its origin. K2 likely hails from the Oort Cloud, a spherical shell of icy debris at the very edge of our solar system, possibly left over from its formation over 4.6 billion years ago. The fact that this comet remained active even in that frigid, distant environment has captured scientists' attention and earned K2 its title as one of the most distant active comets ever observed. As K2 draws closer to the Sun, the frozen materials inside it, including water, carbon dioxide, methane, and ammonia, are vaporized by solar radiation. This process, called sublimation, creates the massive glowing coma and its characteristic tail that can extend for hundreds of thousands of kilometers. In K2's case, estimates suggest that its tail could stretch up to 500,000 miles, a size comparable to Jupiter's diameter. Despite all this, K2 poses no threat to Earth. Scientists confirm there is zero chance of impact. But what makes it even more fascinating is that it continues to be active despite not being as close to the Sun as typical comets are when they begin venting gas. This unusual behavior leads some scientists to believe that other volatile compounds or interactions are at play, possibly hinting at a more complex chemical makeup than previously thought. For the team here at Infinity Beyond, this comet represents more than a scientific event. It's a cosmic reminder of how vast and mysterious our solar system still is. It tells us that even in what we think of as the cold, empty outskirts of space, activity continues in forms we're only beginning to understand. In the next segment, we'll dive deeper into how to observe Comet K2, what time to look, where to look in the sky, and what tools you'll need to catch this ancient wanderer before it vanishes back into the darkness. Stay tuned with Infinity Beyond. As Comet K2 journeyed inward through the solar system, astronomers began noticing something extraordinary. Despite being over 2 billion kilometers from the Sun at the time of discovery, K2 was already active. That activity has only increased as it continues its inward path, forming an impressive coma and a dramatic tail that make it unlike any other comet in recent memory. So, what's causing this comet to behave in such a lively way, even from a distance where most comets would still be frozen and inert? Normally, comets become active, meaning they develop their coma and tail, only after getting significantly closer to the Sun. That's when the Sun's heat causes sublimation, turning the frozen gases inside the comet into gas and dust, which then escape into space and form the iconic features we associate with comets. But Comet K2 defies this expectation. Its coma, which is the cloud of gas and dust surrounding its icy core, is already huge, with estimates suggesting that the dust cloud is almost the size of planet Jupiter. That's a diameter of about 140,000 kilometers, all created just from the comet's internal ice reacting to the increasing heat of the Sun, from very far away. What's even more astonishing is the length of K2's tail. Astronomers believe the tail could stretch as far as 500,000 miles, roughly twice the distance from the Earth to the Moon. That makes it one of the longest cometary tails observed in recent decades. Even more intriguing is the fact that it seems to be in a permanent coma state, meaning the comet is continuously releasing gas and dust at an unusually steady rate, something that suggests there might be more than just solar heating at play. Some experts believe that volatile compounds, chemicals that sublimate at lower temperatures than water ice, could be fueling this activity. These may include carbon monoxide, carbon dioxide, or even ammonia ice, all of which can turn into gas even when a comet is far from the Sun. If these materials are mixed throughout K2's body, they could explain why it has stayed active for such a long time and at such great distances. There's also a chance that K2's nucleus, the solid part of the comet, may be more porous or fragmented than average. This would allow heat to penetrate more deeply into its structure, triggering more sublimation from inside out. However, we still don't know for certain. That's why Comet K2 continues to fascinate researchers. It doesn't behave like most comets we've studied before. As for the true size of K2's nucleus, there's still some debate. Initial estimates from ground-based observations suggested it could be as large as 100 miles wide, which would make it a true giant among comets. However, more accurate data from the Hubble Space Telescope places the size at a more conservative 11 to 12 miles, 18 to 20 kilometers across, still large enough to stack two Mount Everests on top of each other. Regardless of its exact size, one thing is clear. K2 is a rare and fascinating object, possibly unlike any comet we've studied before. It gives scientists a unique opportunity to explore what comets are made of, how they evolve, and how they can remain active even at vast distances from the Sun. At infinity beyond, we believe this makes Comet K2 more than just a bright object in the night sky. It's a mystery waiting to be unraveled, and a messenger from the distant reaches of our solar system. In our next segment, we'll explore what might happen to K2 next. Will it survive its encounter with the Sun, or disintegrate like so many comets before it? Stay tuned. So how and when can we observe this colossal celestial visitor? If you've never seen a comet in your life, this could be your chance, even if it's a subtle one. Comet K2, officially designated C2017 K2, PANSTARRS, is not just rare for its size and origin, but also for how far it's traveled and remained active. Now that it has entered the inner solar system, visibility becomes a critical question. Let's talk about the most important detail: timing. The best period to catch a glimpse of Comet K2 was around July 14, 2022, when it passed closest to Earth. However, it remains visible for several months after that, specifically from May through September 2022, particularly in the Northern Hemisphere. You'll want to observe it during a window between 1 hour after sunset and about 3 a.m., when the skies are darkest and the comet is above the horizon. Next, the location in the sky. The best place to start looking is the constellation Ophiuchus. Also known as the Serpent Bearer, Ophiuchus lies between the constellations of Scorpius and Hercules, in a region of the sky that appears highest during summer nights in the Northern Hemisphere. Star map apps like Stellarium, Sky Safari, or Starwalk can be very helpful. Just input Comet K2 and they'll point you in the right direction. But can we see K2 with the naked eye? Unfortunately, no, or at least not under typical conditions. Astronomers estimated that at its brightest, K2 would reach a magnitude of around 7 to 8. For reference, the human eye can usually see objects up to magnitude 6 in perfect dark skies, and only from very remote locations with little to no light pollution. So, to observe Comet K2, you'll need at least a small telescope. A 4.5-inch reflector telescope is sufficient if you live in a rural or dark area. In urban or suburban environments where light pollution is stronger, a 6-inch or larger telescope will be much more effective. For amateur astronomers and hobbyists, this is a good opportunity to bring out your equipment, especially if you're familiar with tracking faint objects. Currently, as of the last reported magnitude, around 9.0, K2 is just faintly visible using a small telescope in dark rural skies. Its visibility may improve slightly, but it will never become as spectacular or as bright as famous comets like Hale-Bopp or Neowise. What makes K2 exceptional is not its brightness, but rather its story. How something from the farthest reaches of the solar system can still come to life and glow in the night sky. As the comet continues its approach toward the Sun, it may brighten slightly or become more defined in shape. But keep in mind, comets are unpredictable, Solar heat can either activate them more intensely or break them apart. That's why astronomers and skywatchers alike remain cautiously optimistic when it comes to K2's behavior. Here at Infinity Beyond, we recommend preparing your telescope, finding a dark sky location, and setting aside some quiet time under the stars. Even if K2 doesn't impress with brightness, it rewards those who observe patiently, showing us a piece of the solar system's ancient past, still active, still glowing. In the next part, we'll look at the physical composition and mystery behind K2's behavior. Why is this comet so active from such a distance? And could it teach us something new about the chemistry of early solar system objects? Stick around with Infinity Beyond as we unravel the secrets of this icy wanderer. As Comet K2 makes its pass through the inner solar system and begins its long return journey to the darkness of the Oort Cloud, we're left with more than just astronomical data. We're left with a sense of wonder, a deep and profound reminder that we are part of something far greater than ourselves. K2 is not merely a frozen rock drifting through space. It is a time capsule, carrying within it 4.6 billion years of cosmic history. Long before there were humans, before there was Earth as we know it, K2 was already out there, a silent witness to the formation of the solar system. And now, in 2022, we've had the rare opportunity to observe it up close. Through telescopes pointed skyward by both professionals and passionate amateurs, we've traced its coma, measured its tail, and debated its structure. We've watched it defy expectations, becoming active at distances where most comets remain dormant. We've seen it glow and dance in the night sky, even if only faintly, from millions of kilometers away. But beyond the science, Comet K2 offers something deeper. It sparks the kind of existential curiosity that has driven humanity for millennia. When we look at a comet, we're not just looking at a celestial object. We're looking at a fragment of creation, a piece of the original building blocks that may have seeded planets, even life itself. Some scientists believe that comets like K2 may have played a role in delivering water and organic molecules to Earth billions of years ago. In that way, comets aren't just visitors. They might be ancestors, carriers of the ingredients of life, frozen and preserved in the cold for eons, now warming up and reminding us of our beginnings. The journey of K2 reminds us that the solar system is still alive and dynamic. Far from being a static collection of planets, it's a place of motion, change, and unexpected beauty. Each comet that passes us carries its own story, and K2's tale is one of resilience, distance, and ancient mystery. At Infinity Beyond, our mission is to bring the universe closer to you, to transform scientific phenomena into stories of discovery, awe, and reflection. As you watch Comet K2 fade back into the distant reaches of the solar system, know that it's not truly gone. It leaves behind inspiration and a trail of questions that future generations may continue to pursue. So what can we take away from Comet K2? We've learned that activity can emerge from surprising places, that the solar system still holds secrets, even in regions we've barely begun to explore, and that the light of a distant comet, no matter how faint, has the power to stir something deep and timeless within us. Whether you saw it through a telescope or simply heard its story told here, Comet K2 has touched your life, even for just a moment. And in that moment, we are all reminded that we're part of a vast and incredible cosmos, one that continues to surprise and inspire. So keep looking up. The sky has more to show us, and here at Infinity Beyond, we'll be right here, helping you understand it. One comet, one star, one mystery at a time. If you enjoyed this journey through the stars, don't forget to like, subscribe, and share this video. And let us know in the comments, what would you want to see next? From black holes to exoplanets, from ancient light to future missions, the universe awaits. Through Throughout history, the sun has been more than just a celestial body. It has been a symbol, a deity, and a source of awe for countless civilizations. From the towering temples of Egypt to the mountaintop rituals of the Inca, humanity has always sensed that the sun is more than just light. It is life, power, and perhaps judgment. At Infinity Beyond, we pause from the science to reflect on the spiritual and philosophical legacy of our star, and what it tells us about who we are. In ancient Egypt, the sun was Ra, the all-seeing god who sailed across the sky in his solar bark, bringing light by day and battling darkness by night. In Aztec mythology, the sun required constant sacrifice to continue rising, blood for light, in a brutal yet symbolic economy of survival. The Inca Empire worshipped Inti, the sun god, whose divine descendants were believed to be their emperors. The great temple of the sun in Cusco was covered in gold to reflect his glory. Even in Norse mythology, the sun was pursued across the sky by a cosmic wolf, destined to be devoured during Ragnarok, the end of days. The message across cultures is strikingly similar. The sun is sacred, but also dangerous. It gives life, but can also take it away. In philosophy, the sun has been used as a metaphor for truth and enlightenment. Plato compared the sun to the form of the good in his allegory of the cave, what illuminates reality and makes knowledge possible. In Buddhism, the rising sun symbolizes impermanence and renewal, each day a chance to begin again. We see the sun in art, poetry, religion, and science, a constant across cultures, eras, and worldviews. It is both a fact and a feeling. We orbit it physically, but also culturally and emotionally. In modern times, we've stopped worshiping the sun and started ignoring it, at least until it reminds us of its power. Solar flares, blackouts, and geomagnetic storms are a stark reminder that the sun is not tame. It does not rise and set for us. It burns constantly in nuclear fury, oblivious to our cities, our satellites, and our ambitions. At Infinity Beyond, we argue that this disconnect is dangerous. Not because we should go back to sun worship, but because we must return to a sense of respect and humility. Perhaps the most poetic truth is this: the sun is a mirror. Its cycles, storms, and rhythms reflect our own. Just as the sun goes through periods of calm and eruption, so does humanity. Just as it gives life freely, it can also test our resilience. And just as it has shown for 4.6 billion years, it reminds us how brief our time truly is. In our next segment, we'll explore how understanding solar storms and cycles can actually give us a window into the distant future, not just of Earth, but of the sun's eventual death, and what will happen when its light finally fades. Because to know the sun is to know both our origins and our destiny. The sun is not eternal. One day, billions of years from now, its nuclear heart will falter, its fuel will deplete, and its light will dim. At Infinity Beyond, we take you far beyond solar storms and blackouts, into the cosmic future, where the sun's final act begins. Right now, our sun is in the main sequence phase, where it steadily fuses hydrogen into helium in its core. This phase lasts approximately 10 billion years, and we're currently about 4.6 billion years into that journey. But hydrogen is a finite fuel. When it runs out, gravity will take over. The sun's core will contract, heating up until it begins fusing helium into heavier elements like carbon and oxygen. As this happens, the sun's outer layers will expand massively, engulfing Mercury, Venus, and possibly Earth, turning our once warm star into a red giant. Its surface may cool, but its size will increase over 100 times its current diameter. In this swollen state, the sun will vaporize nearby planets and boil Earth's oceans, if our planet survives gravitationally at all. The atmosphere will be stripped away, and any trace of life will vanish. Earth's story will end in fire. Yet ironically, the sun will shine brighter than ever in its final breaths. Not a peaceful fade, but a violent blaze of cosmic transformation. After millions of years in the red giant phase, the sun will finally become unstable, shedding its outer layers in a brilliant wave of gas and plasma. What's left behind is a glowing planetary nebula, a colorful shell of light stretching across space. At its heart remains a white dwarf, a hot, dense core no larger than Earth, but with half the mass of the original sun. This stellar remnant will no longer produce energy. It will simply cool, slowly, for trillions of years. The nebula may eventually seed new stars, new planets, perhaps new life. Though the sun will die, it will not vanish. Its atoms, created in fusion, will spread into the galaxy, becoming part of other systems. The calcium in our bones, the iron in our blood, the carbon in our DNA, all forged in stars like the sun. At Infinity Beyond, we reflect on this poetic cycle. From dust we came, to dust we return, but it's stardust. In our next segment, we'll explore what happens after the sun is gone. What does the future hold for the solar system, the Milky Way, and the universe itself? Because if the death of our star is only one chapter, what comes after could reshape everything we thought we knew about existence. After the sun's death, the solar system will drift into cold silence. The planets, those that survive, will continue orbiting a dark, burnt-out white dwarf, no longer bathed in life-giving light, but held by ghostly gravity. The warmth that once powered atmospheres, oceans, and civilizations will vanish, and our cosmic neighborhood will fall asleep. At Infinity Beyond, we peer into this dark future, not with fear, but with awe. For even in the silence, the story continues. Mercury and Venus will have been consumed. Earth, if not vaporized, will be a barren cinder, frozen, atmosphere lost, tectonically dead. Mars, farther out, may linger longer, but without solar energy, even its once promising surface will become a lifeless tundra. The gas giants, Jupiter and Saturn, may retain their structure for a while, but without energy input, their storms will fade. Their moons, once candidates for life, will freeze solid. Even the Kuiper Belt and Oort Cloud, regions of icy comets, will remain, but in total darkness. The solar system becomes a graveyard, silent and static. Yet in this stillness lies something profound: cosmic memory. The sun's core, now a white dwarf, will shine faintly for billions of years, slowly cooling into a black dwarf, a hypothetical object no one has ever seen, because the universe isn't old enough yet for one to exist. It won't explode, it won't collapse. It will simply fade, pixel by pixel, into thermodynamic equilibrium, a cosmic death by stillness. But this white dwarf still contains the story of our star, like the final glowing ember in a dying campfire. Even as our sun fades, the Milky Way continues to spin, and other stars will rise, die, and be reborn. In 4 billion years, our galaxy is expected to collide with Andromeda, forming a massive elliptical galaxy that will reshape stellar life forever. Earth will be long gone, but its atoms may find their way into new worlds, new suns, perhaps even new forms of life. As Carl Sagan once said, we are a way for the cosmos to know itself. What does the sun leave behind? Not just light, heat, or particles. It leaves behind us, creatures born from its elements, thinkers who built telescopes to stare back at it, storytellers who turned its fire into poetry. At Infinity Beyond, we believe that even in death, the sun is eternal, because its existence echoes in everything we are and everything we may become. In the next segment, we'll zoom out even further into the fate of the universe itself. Will it end in fire, ice, or something stranger? Because if stars like our sun die, what happens when the last star goes out? One day, trillions upon trillions of years from now, The last star in the universe will burn its final atom of fuel. No more nuclear fusion, no more radiant heat, no more light in the void. The universe, once ablaze with galaxies, stars, and suns, will enter its final chapter, the era of degeneracy. At Infinity Beyond, we invite you into this haunting cosmic dusk, where even light itself is a memory. After the last red dwarfs flicker out, only remnants of stellar evolution remain. White dwarfs, neutron stars, black holes. These objects are no longer alive in the stellar sense. They do not shine, grow, or burn. They endure. Galaxies become invisible. Planetary systems become unbound. The cosmos grows darker and colder, every second stretched by an expanding fabric of space. In this far future darkness, black holes rule. They roam silently, consuming matter, colliding with one another, forming ever more massive singularities. Some black holes will merge into supermassive giants, hiding quietly in the darkness. They are not evil. They are entropy in motion. But even black holes are not eternal. Thanks to Stephen Hawking's theory of Hawking radiation, black holes will slowly lose mass, emitting faint particles across eons. Over time, unimaginably long stretches of time, they too will evaporate. The last great fireworks of the universe will be the final quantum whispers of dying black holes. At this point, time becomes meaningless to humans. We measure years by orbits, by suns, by shadows, none of which remain. What will exist then? Dark matter and energy still permeating space-time. A few lonely subatomic particles, the fossil ruins of what once was a brilliant, creative universe. No observers, no life, no heat, no structure, just stillness. In the heart of our solar system resides an unlikely killer, one that gives life but can also destroy it. Our sun, the glowing beacon of warmth and vitality, holds within it a raw and untamed power capable of shaking Earth's technological foundations. History has already shown us a glimpse of this devastating potential. Back in August 4, 1972, during the tense days of the Vietnam War, U.S. Task Force 7 aircraft were flying reconnaissance missions off the coast of North Vietnam. Everything appeared normal, clear skies, calm waters, until chaos erupted. In mere seconds, 20 to 30 underwater explosions went off in Haiphong Harbor. These weren't enemy attacks. The cause was baffling. The mines planted there were part of Operation Pocket Money, a strategic U.S. naval effort to blockade North Vietnamese maritime routes. These magnetic mines were designed to detonate when triggered by the metallic hull of a passing ship, disturbing the magnetic field. But no ships passed overhead. So why did the mines explode? For over 40 years, the answer remained a mystery. That is, until recently, when declassified U.S. Navy reports unveiled a shocking culprit, not of this Earth, but from above. The Sun. This revelation reframed everything we thought we knew about space weather's impact on military and technology. Solar activity, often underestimated, had enough force to trip underwater munitions. This unprecedented event set scientists scrambling to understand just how far solar storms could reach and how deadly they could be. Historically, the sun has been both worshipped and feared. To the ancient Egyptians, it was personified by Ra, the sun god, depicted with a falcon's head and a solar disk resting on his crown. Ra symbolized the giver of life, warmth, light, and nourishment. But he also carried a darker side, one of destruction and wrath. His eye, in the mythological texts, could manifest as a fiery lioness to scorch the earth when he was displeased. This ancient allegory is eerily resonant in our modern age. The sun, so essential to life, still holds the power to unleash catastrophe. And today, that risk is higher than ever. We are currently entering solar cycle 25, a period predicted to be more active than its predecessors. Scientists expected a maximum of around 125 sunspots per month, but the Sun has defied forecasts, showing signs it may peak closer to 200. This rise in solar activity increases the probability of solar storms, flares, and coronal mass ejections, explosions that could severely damage satellites, GPS systems, aviation controls, and entire power grids. While the general public may only notice a faint aurora in the sky during such events, these storms have the potential to shut down financial systems, interrupt military communications, and plunge cities into darkness. The incident of 1972 was just a small taste of what's possible. Today, the stakes are unimaginably higher. At Infinity Beyond, we explore this cosmic tension, the balance between the Sun's life-giving light and its capacity for annihilation. In upcoming episodes, we'll delve deeper into solar cycles, magnetic fields, historic solar catastrophes, and what agencies like NASA are doing to protect humanity from the Sun's fury. Because make no mistake, it's not a question of if the next solar storm will strike. It's a question of when. About 4.6 billion years ago, long before Earth harbored any life, a massive molecular cloud of gas and dust began collapsing under its own weight. The collapse wasn't spontaneous. It may have been triggered by shockwaves from a nearby supernova or the gravitational influence of a cluster of young stars. Whatever the cause, this cosmic event set the stage for something monumental, the birth of our Sun. As the cloud contracted, it began to spin faster, just like a spinning figure skater pulling in their arms. This rotation caused the cloud to flatten into a disk, a process governed by the conservation of angular momentum. In the center of this disk, matter started clumping together under gravity's relentless pull. This central core became denser and hotter over time, accumulating more material and increasing in mass. Eventually, the temperature inside this core soared into the millions of degrees. That's when something truly extraordinary happened. Nuclear fusion began. Hydrogen atoms collided with such immense force that they fused into helium, releasing staggering amounts of energy. This energy pushed outward, counterbalancing the inward pull of gravity. And just like that, a new star was born. Our Sun. The Sun entered what astronomers call the main sequence phase, a long and stable period where fusion sustains its shine. And it's still in that phase today, but this apparent stability hides the tremendous power it holds. Every second, the Sun emits more energy than humanity has ever consumed in its entire existence. It bathes the Earth in light and warmth, fueling life as we know it. Through photosynthesis, plants convert sunlight into food, sustaining every living being along the food chain, including us. But this nurturing energy is only part of the Sun's story. The same processes that give us light also produce intense solar winds, streams of charged particles ejected from the Sun's corona, its outermost layer. These particles move at tremendous speeds, carried along magnetic field lines stretching across the solar system. The Earth's magnetic field acts as a shield, protecting us from most of these charged particles. But sometimes, the Sun unleashes more than just a breeze. It roars. When these solar winds intensify, they can cause geomagnetic storms, disrupting satellite communication, electrical grids, and even global positioning systems. They also create stunning auroras, lighting up the sky with vivid colors: red from nitrogen, green from oxygen, and blue from hydrogen. These lights are beautiful, but they signal a deeper, invisible force interacting with our planet's magnetic barrier. And there's more. Solar magnetic fields don't stay neatly aligned. The Sun's rotation causes its equator to spin faster than its poles, twisting its magnetic field into knots. Over time, these knots can snap, releasing immense bursts of energy in what we call solar flares or coronal mass ejections, CMEs. When Earth lies in the path of a CEOW, the consequences can be severe. At Infinity Beyond, we're only beginning to uncover how intimately our fate is tied to the Sun's moods. In the next chapter, we'll dive deeper into how these solar storms form and how a single misaligned flare could plunge Earth into a technological blackout. Because this story isn't ancient myth, it's modern science with real consequences. Fast forward to today, our Sun has reached the midpoint of its life cycle, around 4.6 billion years old, and it's currently in what scientists refer to as the main sequence phase. During this stage, it shines stably and consistently, providing a nurturing environment for life to flourish on Earth. However, the stability we enjoy is balanced atop a system of intense and dynamic activity beneath the surface. Activity we are only just beginning to understand. The Sun today is approximately 30% more luminous than when it was born. Its energy flows through the solar system in the form of light and heat, supporting nearly every living process on Earth. It drives photosynthesis in plants, controls weather systems, and ultimately determines the rhythms of ecosystems. Solar radiation is, quite literally, the foundation of all life as we know it. Every bite of food we consume, every breath of oxygen we take, can be traced back to that golden sphere hanging in our sky. But despite its life-giving role, the Sun harbors secrets. Hidden within its surface are volatile magnetic fields and extreme heat zones that can become dangerous without warning. When viewed through the eyes of space observatories, this glowing star reveals an entirely different face. It's not the gentle celestial guardian we imagine. Instead, it's a raging, violent engine of energy, a star capable of producing the most powerful explosions in our entire solar system. Every second, more energy is generated through solar activity than all of human history's consumption combined. Most of the time, that energy flows outward smoothly, bathing Earth in light. But sometimes it becomes trapped and twisted into unstable magnetic loops near sunspots. These sunspots are cooler, darker areas on the Sun's surface, but they are surrounded by highly active magnetic regions. A massive blackout triggered by a solar storm wouldn't just plunge cities into darkness, it would send shockwaves through every aspect of modern civilization. Unlike local outages caused by weather or equipment failure, a Carrington-level event could knock out power grids on multiple continents simultaneously, triggering a chain reaction of global disruption. At Infinity Beyond, we trace what would happen hour by hour as the modern world loses its most essential lifeline: electricity. Within the first minutes, internet servers go down. Data centers, even those with backup systems, begin shutting off non-essential operations. Air traffic control loses contact with multiple aircraft. Hospitals, overwhelmed with emergency cases, begin triaging power use. In less than an hour, banks suspend transactions. ATMs go dark. Stock markets around the world cease trading, either through algorithmic failure or power loss. Water pumping stations, reliant on electric motors, stop functioning. Taps run dry. Gas stations can't operate pumps. Vehicles stall. Deliveries halt. Fuel supplies begin to choke. After 24 hours, cities are in chaos. Refrigerators fail, spoiling food. Security systems, including cameras and alarms, go offline. Cell towers and Wi-Fi routers stop working, rendering communication nearly impossible. Satellites, without proper shielding, suffer cascading failures. GPS becomes unreliable. And after a few days, the deeper, slower crises begin to take shape. Hospitals run out of generator fuel. Supply chains collapse, affecting everything from food to medicine. Public trust deteriorates, giving way to panic buying, looting, and misinformation. digital money becomes meaningless as banks remain offline and no transactions can be processed. Even your smartphone, fully charged, becomes a glorified flashlight once networks vanish. At Infinity Beyond, we explore how fragile our modern society really is. It's not just our comfort that depends on electricity. It's survival. In the age of the cloud, even critical infrastructure like traffic lights, emergency broadcast systems, and police databases depend on centralized servers powered by electricity. A blackout of this scale would also paralyze governments. With no internet, no real-time updates, and no command centers, decision-making reverts to pre-digital methods. Paper, radios, in some areas, nothing at all. One of the lesser-known consequences is the psychological effect. With no light pollution and communication outages, people may look up at the night sky for the first time in years, only to see nothing moving, no aircraft, no satellites, just silence. A world unplugged. Yet there is hope. Some nations, like Sweden, Germany, and South Korea, have begun building hardened microgrids, localized power systems that can operate independently. Others are exploring low Earth orbit satellites resistant to radiation storms. The key to survival isn't preventing the storm, it's preparing for it. In our next segment, we'll investigate how the sun's impact on Earth might even extend to triggering earthquakes, and how researchers are discovering strange correlations between solar activity and geophysical disasters. Because when the lights go out, the Earth itself may begin to tremble. For decades, researchers have quietly noted a strange and unsettling correlation. Periods of heightened solar activity, especially intense solar flares and geomagnetic storms, often align with major earthquakes on Earth. While causation hasn't been conclusively proven, the patterns are too consistent to ignore. At Infinity Beyond, we explore this eerie link between space and seismic chaos, a relationship that could reshape how we view Earth's internal stability. The theory goes like this: when the sun releases a coronal mass ejection, CME, it sends an immense wave of charged particles toward Earth. Upon impact, these particles don't just interact with satellites and power lines, they also penetrate Earth's magnetosphere and ionosphere, triggering changes in atmospheric pressure and electromagnetic stress in the crust. Think of Earth as a stretched rubber band. Over millions of years, tectonic plates grind and build tension. But could external geomagnetic pressure act as the final nudge that snaps the band? Some researchers say yes. One of the most striking examples occurred just months before the devastating 2004 Indian Ocean earthquake and tsunami, which measured 9.1 on the Richter scale and killed over 283,000 people. That year, the sun released an unusually powerful X-class solar flare, which triggered strong geomagnetic storms on Earth. Other instances, like the 2011 Tohoku earthquake in Japan and the 2010 Chile earthquake, were also preceded by bursts of solar activity. In each case, the solar events preceded tectonic events by days or hours, leading some geophysicists to speculate that electromagnetic interference may contribute to fault destabilization. Of course, this theory remains controversial. Skeptics argue that earthquakes have occurred for billions of years, long before human beings tracked the sun. But proponents of the idea counter that solar-triggered earthquakes don't create new faults. They simply accelerate the failure of already stressed zones, acting as a cosmic catalyst for an already inevitable event. At Infinity Beyond, we believe this question is more than academic. If proven, this link could revolutionize earthquake prediction, adding solar activity as a key warning factor for seismic hotspots like California, Indonesia, and the Pacific Ring of Fire. Government agencies and research institutes are starting to take notice. Japan's National Institute of Information and Communications Technology, NICT, has begun integrating space weather data into early earthquake models. Meanwhile, NASA's Heliospheric Division is funding research on the geo-effectiveness of magnetic perturbations on tectonic regions. Could the Sun be Earth's invisible finger on the trigger? It wouldn't be the first time celestial bodies have influenced geology. The Moon causes tides. Jupiter affects comet paths. It may be time to accept that the Sun does more than shine. It may shake the ground beneath our feet. In our next segment, we'll bring this all together. From satellites falling from the sky, to pacemakers malfunctioning, to blackouts and earthquakes, what does a worst-case scenario solar storm actually look like? Because one day, all these warnings may converge. And when they do, it won't just be a bad day on Earth. It will be the day the Sun strikes. Let's imagine the worst-case scenario. A Carrington-level coronal mass ejection, CME, the most violent class of solar storm, launched directly at Earth in the year 2020, right as we enter the peak of solar cycle 25. The Sun ejects billions of tons of electrified plasma, moving at 2,000 kilometers per second, headed straight for our planet. And this time, we're not on the lucky side of orbit. At Infinity Beyond, we walk you through what this day could look like, not to cause fear, but to help the world understand the stakes. Hour 0. Impact. NASA satellites detect a fast-approaching CME, but because solar flares travel at the speed of light, the X-ray burst has already hit, causing radio blackouts worldwide. High-frequency communications vanish. Transpolar flights lose contact. GPS systems show glitches and drifts, confusing navigation systems. Hour 1. The shock wave. The CME slams into Earth's magnetosphere. Geomagnetic storms rage. Satellites begin failing, either knocked out of orbit or bombarded by radiation. Weather data, financial transactions, global positioning, all disrupted. Some SpaceX Starlink satellites are pushed into atmospheric decay. Internet service begins to drop. Hour 3. Power grid chaos. Transformers start to hum, spark, and in some cases, explode. Canada's grid goes down. Sections of Northern Europe begin failing. U.S. power companies issue rolling blackouts to protect the infrastructure. But some areas, especially along long transmission lines, are hit hard. Hospitals rely on backup generators. Water purification systems stall. Cell towers begin to die. The world begins to disconnect. Even worse, flares are often accompanied by coronal mass ejection, CMEs. While the flare arrives immediately, the CME, moving slower, slams into Earth hours or days later, like a second wave, triggering geomagnetic storms that can disable power grids and satellites. Solar physicists constantly monitor the Sun's magnetic fields, searching for signs of instability. The presence of large, complex sunspots, cooler, magnetically active regions on the solar surface, often precedes an X-class flare. The more twisted and chaotic the magnetic loops, the higher the chance of a major release. At Infinity Beyond, we examine how space weather forecasters are racing to improve flare prediction. Satellites like NASA's Solar Dynamics Observatory, SDO, and SOHO, Solar and Heliospheric Observatory, provide high-resolution imagery and magnetometric data, helping us spot trouble before it strikes. But even with this technology, we still lack accurate short-term forecasts. So far, the only truly reliable method of protection is preparedness. Hardened satellite systems, resilient power grids, and public awareness are crucial. Because once an X-class flare is detected, it's already here. In our next segment, we'll look at how solar flares have impacted modern transportation, including shocking incidents where passenger planes and even life-saving medical devices were disrupted mid-flight. Because the Sun doesn't just threaten space, it's already knocking on our airplane doors. In 2016, cybersecurity researcher Marie Moe boarded a flight, unaware that her own heartbeat was about to reveal the invisible reach of the sun. Mid-flight, she began to feel something strange, a rapid, involuntary twitching in her chest. It was her pacemaker. Designed to regulate her heart rhythm, it suddenly switched to backup mode. Upon landing, a diagnostics check revealed that one of the device's memory bits had flipped, altered without warning, likely by an external energy burst. This phenomenon is known in computing as a single event upset, SEU, or more colloquially, a bit flip. It occurs when high-energy particles, often from cosmic rays or solar flares, strike microchips, altering stored binary values. In this case, it changed a 0 to a 1, causing the pacemaker to reset. Though impossible to definitively trace to a specific solar event, Moe's experience isn't isolated. At Infinity Beyond, we've investigated multiple such incidents that show how deeply solar activity can infiltrate modern life support systems. In 2008, a Qantas Airways flight over Western Australia suddenly plunged hundreds of feet, twice, injuring passengers and terrifying crew. The culprit? A software glitch in the aircraft's inertial reference system, likely triggered by a similar radiation-induced memory error. Both cases point to a sobering truth. Solar flares can affect us even inside airplanes at cruising altitude. And the higher we fly, the less protection Earth's atmosphere provides against incoming radiation. Modern jetliners often cruise at 35,000 feet, well within reach of high-energy particles from strong solar events. Radiation exposure at these altitudes is still relatively low, but during intense solar storms, especially X-class flares, the dose can rise significantly. Airline crews, pregnant women, and frequent flyers face greater risks. And that's why some airlines now reroute transpolar flights during major solar activity to minimize exposure. But the impact isn't limited to aviation. Hospitals, military systems, and data centers all rely on vulnerable electronics. Even self-driving cars, drones, and smart home devices contain microchips susceptible to SEUs. In an increasingly digital world, these silent attacks from space are becoming more than rare anomalies. They're emerging as systemic risks. At Infinity Beyond, we believe that public awareness is just as important as satellite monitoring. While large-scale infrastructure failures are dramatic, it's the smaller, personal-level vulnerabilities that go unnoticed until they strike. Imagine the scenario: a patient undergoing surgery, a pilot flying through polar skies, a drone delivering emergency medicine. A solar flare surges, and in an instant, bits flip. This isn't science fiction. It's already happened. As our society integrates AI, autonomous systems, and real-time decision-making electronics, the consequences of cosmic interference are magnified. Without proper radiation shielding, error correction systems, and resilient chip designs, we are building a fragile world under an unpredictable sky. In our next segment, we'll journey back to one of the most mysterious episodes in modern warfare: the unexplained detonation of underwater mines during the Vietnam War, finally linked to a solar storm after decades of confusion. Because the sun doesn't choose its targets, it strikes everything, from satellites to your heartbeat. During the Vietnam War, a baffling incident left military experts scratching their heads for decades. On August 4, 1972, a squadron from the U.S. Task Force 77 was flying routine missions over Haiphong Harbor when, without any enemy activity nearby, 20 to 30 underwater explosions erupted almost simultaneously. These weren't bombs dropped from planes. These were U.S.-planted naval mines, part of Operation Pocket Money, a campaign to blockade North Vietnam by sea. What puzzled the military was that no ships had triggered these mines. They had been carefully designed to detonate only when a magnetic field disturbance, such as that caused by a passing vessel, was detected. So how had they all exploded at once, under clear skies and calm waters? For over 40 years, the cause remained a mystery. That is, until a recent study, accepted by the journal Space Weather, uncovered a startling explanation. The culprit was the Sun. At Infinity Beyond, we uncover how this single event reshaped our understanding of space warfare. In the days leading up to the incident, a massive sunspot region, catalogued as MR11976, had become highly active. On August 2nd and the 3rd, it unleashed a series of brilliant solar flares and coronal mass ejections, CMEs, one of which was Earth-directed. This solar storm was powerful enough to disrupt the planet's magnetic field, including the waters of Haiphong Harbor. The resulting geomagnetic disturbance may have been strong enough to trigger the magnetic sensors inside the mines, tricking them into thinking a ship was passing overhead. Boom! The mines detonated, simultaneously, automatically, and inexplicably, until now. This moment marks one of the first known instances in which solar activity directly affected military hardware, possibly altering the outcome of a tactical mission. And if it happened then, it can happen again. Modern militaries around the world rely heavily on magnetically triggered weaponry, communication satellites, GPS-guided munitions, and real-time battlefield data systems. All of these are susceptible to space weather events. Imagine a missile system being blinded, a drone fleet going offline, a stealth submarine losing communication. When space weather intervenes, strategic advantage becomes chaos. At Infinity Beyond, we urge defense sectors worldwide to recognize that solar storms are not just scientific curiosities, they're national security threats. While traditional military training prepares for terrestrial threats, space weather remains a blind spot in many defense protocols. Today, with the increasing use of AI-driven decision systems, the threat compounds. A well-timed solar flare could corrupt data mid-transfer, flip command codes, or disable surveillance satellites, all without a single human error or enemy missile. And yet, despite the risk, global militaries are only beginning to incorporate space weather forecasts into strategic planning. NASA, NOAA, and other agencies now provide real-time alerts, but the reaction time is often limited, especially for systems deployed in remote or space-based theaters. In our next segment, we'll shift from war to communication, how telegraph lines in 1859 caught fire, and how satellites today face similar dangers from the same cosmic source. Because the battlefield is no longer just land, sea, and sky, it now includes the space between stars. March 13, 1989. It was still winter in Canada. Snow blanketed the cities, and the temperature hovered below freezing. At 2:44 a.m., without warning, the entire province of Quebec went dark. Lights flickered and died. Power plants shut down. More than 6 million people were suddenly without electricity. No heating, no communication, no running water. The culprit? Not a cyber attack, not terrorism, not human error. It was the Sun. Just hours earlier, the Sun had released a massive coronal mass ejection, CMEO, launching billions of tons of plasma and magnetic energy toward Earth. Traveling at over 2,000 kilometers per second, the wave slammed into Earth's magnetic field, generating powerful electric currents across the planet's surface. In Quebec, those geomagnetically induced currents, GICs, surged into the regional power grid, overloading transformers and tripping protective circuits. In less than 90 seconds, the entire grid collapsed. Across the province, elevators stalled, traffic lights went dead, radio towers fell silent, and emergency services were paralyzed. At Infinity Beyond, we emphasize that this wasn't just a freak event, it was a preview of the future. Quebec's blackout demonstrated just how quickly space weather can overwhelm our infrastructure. Despite its modern electrical system, the province had no defense against a geomagnetic storm. And Quebec wasn't the only region affected. Northeastern parts of the United States also reported electrical anomalies. The only reason they didn't face full blackouts was that their grids were better interconnected, able to absorb and redirect the surge. But what if the storm had been just a bit stronger? Experts later warned that a more intense storm could have caused permanent damage to transformers, not just shutting them down temporarily, but melting them from the inside out. Replacing these massive units can take months or even years, especially in remote regions or during widespread failures. In a worst-case scenario, large portions of North America could have remained dark for weeks, plunging society into economic chaos. And that was in 1989, before the internet became the backbone of global communication, before cloud storage, before GPS-controlled agriculture, aviation, and finance. Today, the risks are even greater. As solar activity increases during solar cycle 25, scientists warn that power grids around the world, especially those in higher latitudes like Canada, Scandinavia, and Northern Europe, remain extremely vulnerable. In fact, some countries have begun to upgrade their transformers and implement protective switching systems that can disconnect sensitive components in the event of a solar storm. In the United Kingdom, for instance, the national grid has begun replacing older equipment and developing contingency plans. In the United States, agencies like NOAA and USGS monitor solar activity in real time, issuing alerts to grid operators when high-energy events are detected. But these systems are only effective if there's advance notice. A fast-moving CME, like the one in 1989, can give us less than 24 hours to prepare. At Infinity Beyond, we explore these fragile connections between the cosmos and our civilization. The blackout in Quebec was just a warning shot. As our world grows more reliant on digital systems, a single solar storm could bring it all crashing down. In the next segment, we'll investigate the near miss of 2012 in more detail, and what would have happened if Earth had been just a few degrees closer in its orbit. Because one thing is certain, the sun has no politics, no preference, no mercy, only power. July 23, 2012. A date that should have gone down in history, but instead became the greatest near-miss humanity has ever experienced. On that day, the sun unleashed two of the most powerful coronal mass ejection CMEs ever observed in the modern space age. These outbursts didn't just burst, they collided with one another in space, forming a supercharged cloud of plasma hurtling toward Earth's orbit. Had this event occurred just 9 days earlier, Earth would have been directly in its path. According to a joint NASA and University of California study, the storm's strength was comparable to the Carrington event of 1859, but its speed and energy output were even more extreme. The CME traveled at 2,850 kilometers per second, one of the fastest solar storms ever recorded. Fortunately, Earth was on the opposite side of the sun's rotational alignment at the time. That simple timing, pure cosmic coincidence, may have saved modern civilization. At Infinity Beyond, we often ask not just what happened, but what if? If Earth had been struck directly, the impact would have been immediate and devastating. Satellites would have failed across every orbital layer. GPS signals, relied on by airlines, shipping companies, agriculture, and global logistics, would have been severely disrupted or lost entirely. Navigation systems would go dark. Communication satellites would fall out of sync. Even the International Space Station may have had to enter emergency mode. And that's just above the atmosphere. On Earth, transformers across power grids in North America, Europe, and Asia would have faced saturation from geomagnetically induced currents, leading to overheating, breakdowns, and in worst cases, explosions. Local blackouts would cascade into continent-wide failures. Water pumping stations, ATMs, hospitals, and data centers, anything that relies on electricity, would be paralyzed. But it doesn't end there. The internet itself, especially its undersea cable network, would be vulnerable. While optical fibers are generally resistant to electromagnetic interference, the repeaters, electronic devices that boost signals across long distances, are not. A storm of this magnitude could compromise the internet at its physical core, leading to a global internet outage lasting weeks or months. Economists estimate that the global financial loss could have exceeded $2 trillion in just the first year alone. Insurance giants may collapse under the weight of claims. Supply chains would stall. Markets would crash. And even food distribution would grind to a halt in urban centers where logistics rely on just-in-time systems. In short, society would reset. And here's the most alarming part. The 2012 CME went almost entirely unreported in mainstream media. Only scientists and space weather agencies fully understood its scale and consequences. The general public remained unaware of how close we came to disaster. No headlines, no emergency meetings, no global response drills. At Infinity Beyond, we shine a light on these silent warnings. The sun doesn't just give us life, it holds the power to take it back in an instant. The 2012 storm was not an isolated event. It was a glimpse into what could and one day will strike again. In our next episode, we'll dive into the solar flare classification system from B to C to the terrifying X class, and explore how scientists rank the energy of the sun's tantrums. Because in the language of stars, X marks the spot where technology meets extinction. To better understand and track solar storms, scientists use a classification system to rank solar flares. Intense bursts of radiation from the sun's surface. These are divided into 4 primary classes: B, C, M, and X, with each letter representing a 10-fold increase in energy from the one before it. B-class flares are the smallest and weakest. C-class flares are minor, often undetectable without scientific instruments. M-class flares can cause brief radio blackouts at Earth's poles and minor radiation storms. But then there's X-class, the monsters of the solar world. X-class flares are the most powerful explosions the sun can produce. And even within the X-class, scientists use a numeric scale from 1 to 9 to rate severity. An X9 is far more dangerous than an X1. In fact, some solar flares exceed even X9, entering extreme, rarely seen territory. At Infinity Beyond, we explore why these numbers matter more than ever in a hyper-connected world. Let's put it in perspective. The Carrington event of 1859 was estimated to be around X45, by far the most powerful flare ever witnessed by humankind. It released enough energy to power the entire modern United States for over 1 million years. The 1989 Quebec blackout was caused by an X1.4 class flare, and the near miss in 2012? It was likely between X20 and X28. These aren't just data points, they're a countdown. The power of an X-class flare lies in what it carries: radioactive particles, X-rays, and extreme ultraviolet radiation. These emissions move at the speed of light, meaning we receive zero warning. When such a flare erupts and is Earth-directed, the effects are instantaneous, causing radio blackouts, communication failures, and GPS disruption within minutes. Imagine a world where planes lose guidance mid-air, financial transactions are frozen, hospitals lose power to life-saving equipment, and people everywhere are plunged into darkness without warning. Chaos, panic, and looting could erupt in cities where electricity powers both information and order. According to a 2013 NASA-funded study, a storm like the one in 2012 could cost the global economy up to $2.6 trillion, with recovery time spanning a full decade. Unlike 1859, we are now hyper-connected, and that connectivity is our vulnerability. What's even more alarming is that we didn't see it coming in time. The 2012 near miss made one thing clear. While we have made strides in solar monitoring, we are still playing catch-up with nature's wrath. The sun does not operate on human schedules. It doesn't wait for our infrastructure to be ready. It simply acts. At Infinity Beyond, our mission is to uncover these warning signs and make them known. The 2012 solar storm wasn't just a missed disaster, it was a message. A reminder from the sun itself that luck is not a strategy. Preparation is the only defense. In the next segment, we'll explore how even minor solar flares have caused real-world incidents, from crashing satellites to triggering pacemaker failures on airplanes, and how, without visible warning, we are all vulnerable to an invisible threat from above. Because if a storm like 2012 happens again, and this time we're in the path, the world will change in a single day. The sun's activity doesn't just threaten satellites or power grids. It can also influence the most fragile systems of all, our biology and our health. Though we often associate space weather with technology, its reach is far greater. In recent years, scientists and medical professionals have begun identifying disturbing connections between solar storms and human physiology. Take, for instance, the case of Marie Moe, a cybersecurity researcher who experienced a terrifying episode in 2016. While flying to Amsterdam, she noticed her pacemaker began malfunctioning. Her chest muscles twitched involuntarily, and she felt an unnatural sensation. When she landed, the pacemaker's diagnostics showed that a crucial bit in its memory had flipped, a phenomenon known as a bit flip, likely caused by a burst of cosmic radiation. Though unprovable in a court of science, since such high-energy particles leave no physical trace, the incident is far from isolated. In fact, bit flips have been documented in everything from hospital equipment to airplane avionics. A 2008 Qantas Airways flight over Western Australia suddenly dropped several hundred feet, twice, injuring dozens. Investigators suspected a similar cause: high-altitude exposure to solar radiation triggering faults in the aircraft systems. At Infinity Beyond, we believe these stories reveal a haunting truth, that the sun's invisible hand can reach even into our bodies and our machines. Unlike lightning or earthquakes, solar radiation arrives silently, without warning, and its impact is increasingly being felt in ways we're only beginning to measure. But it doesn't stop with health. Solar storms have also played a hidden role in military history. Let's return to the Vietnam War. For decades, military analysts were baffled by the sudden explosion of underwater mines in Haiphong Harbor in 1972. These mines were magnetic, designed to detect ships, but no ships had passed. What caused them to detonate? Only recently did a study published in the Journal of Space Weather provide a clue. It pointed to a powerful solar storm that struck Earth at that time. A sunspot region known as MR 11976 had unleashed a series of solar flares and CMEs. The storm reached Earth in just over 14 hours, faster than usual, and may have tripped the magnetic sensors on the mines, detonating them prematurely. This revelation changed our understanding of solar influence. It showed that solar storms could, quite literally, change the course of war. And if they could impact military hardware in the 1970s, imagine what they could do to the global digital infrastructure of 2025. At Infinity Beyond, we examine these connections not just to raise alarms, but to foster awareness. If a solar storm can trigger a pacemaker, down a passenger aircraft, and sabotage naval mines, then what else might it do? The sun may be 150 million kilometers away, but it is not distant in its effects. In our next chapter, we'll turn to the skies, to the astronauts orbiting Earth, and those who will walk on the Moon or Mars in the coming decades. How vulnerable are they to solar radiation? And what would happen if a solar flare struck while humans were on the lunar surface? Because space exploration without space weather protection is a gamble humanity cannot afford. Imagine astronauts standing on the moon's surface, carefully collecting samples, scanning the horizon, communicating with mission control. The sun is shining, space is calm, but suddenly, from 150 million kilometers away, a coronal mass ejection, CME, is launched with ferocious speed. There's no sound, no warning visible to the naked eye. But a storm is coming, and there is no magnetic field on the moon to protect them. This is not science fiction. It's a scenario NASA takes very seriously. Unlike Earth, the moon has no atmosphere and no global magnetic shield. When a solar flare or CME strikes, lethal radiation penetrates the surface with full force. In the case of a direct hit, astronauts exposed on the moon would suffer acute radiation sickness, potentially fatal in just a few hours without proper shelter. Long-term exposure increases the risk of cancer, organ damage, and severe DNA mutation. During the Apollo era, NASA meticulously scheduled missions to avoid periods of heightened solar activity. It was a calculated risk that, in hindsight, was extremely fortunate. None of the missions encountered a major flare. But future missions, such as NASA's upcoming Artemis program or proposed Mars expeditions, will face far longer exposure times, increasing the probability of disaster unless proper shielding and forecasting are in place. At Infinity Beyond, we explore these risks not to scare, but to prepare. Even aboard the International Space Station, ISS, which orbits within Earth's magnetic field, astronauts still receive doses of radiation far above what we experience on the ground. The ISS is equipped with heavy shielding, and crew members take refuge in specially protected modules when solar storms are detected. But what about deep space, or planetary outposts? This brings us to one of the great challenges of 21st century spaceflight: space weather prediction. A CME takes anywhere from 15 to 72 hours to reach Earth after an eruption, but solar flares, carrying harmful X-rays and energetic particles, travel at the speed of light. That means by the time we detect them, it's already too late. That's why early warning systems, like NASA's Parker Solar Probe and NOAA's space weather satellites, are so vital. These instruments monitor the sun's surface in real time, tracking sunspots and magnetic loops where flares are likely to erupt. But even with this vigilance, we still lack a comprehensive global alarm system, something akin to a tornado siren for solar storms. Imagine a future where astronauts on Mars receive a solar siren warning via AI systems that analyze solar activity in real time, giving them minutes to rush into underground bunkers or shielded habitats. That future is not far off. NASA is currently working on an AI-powered system called DAGGER, Deep Learning Geomagnetic Perturbation, which may one day give Earth and space travelers a 30-minute head start before a storm strikes. At Infinity Beyond, we believe awareness is the first defense. As humans push farther into the cosmos, understanding the sun's wrath will be as critical as designing rockets. Because in the vacuum of space, radiation doesn't knock. It arrives uninvited and unseen. In our next episode, we'll return to Earth and explore how geomagnetic storms have already disrupted entire regions, like the 1989 blackout in Quebec, and how power grids across the globe remain vulnerable even today. Because as we venture into new worlds, the one thing we cannot escape is the star we were born from. These findings are feeding into models like DAGGER, refining our ability to predict space weather in real time. Every flyby, Parker gets closer, faster, and more precise. Its final orbit, set for 2025, will be the most intimate brush with a star any spacecraft has ever attempted. At Infinity Beyond, We marvel at the irony. To protect Earth, we had to leave it. To shield ourselves from the sun, we had to fly into its fire. The Parker Solar Probe is a message in reverse. A digital bottle hurled into the sun's inferno to return with knowledge that could one day save civilization. In our next segment, we'll explore the concept of solar sirens, how future infrastructure, from power grids to satellite networks, could be outfitted with early warning systems modeled after tornado alarms to respond instantly to solar threats. Because the future of Earth may not be decided by war or politics, but by a warning light blinking from 150 million kilometers away. NASA envisions a future where solar storm sirens may become as common and as crucial as tornado alarms in storm-prone regions. A world where power stations, satellite control centers, and even spaceports can receive real-time alerts and initiate automatic responses within minutes of solar threats being detected. At Infinity Beyond, we believe this vision isn't just ambitious, it's essential. Unlike hurricanes or tsunamis, solar storms don't produce sound, winds, or visible waves. Their most dangerous emissions, X-rays, gamma rays, and charged particles, race toward Earth at incredible speeds, often faster than our current infrastructure can react. That's why scientists are developing AI-based detection models like Dagger, which we introduced earlier, to close that reaction gap. But NASA wants to go further, to install systems that can act autonomously. Imagine this scenario. A satellite in geosynchronous orbit detects a sudden shift in solar wind direction and intensity. That data is instantly analyzed by an AI model trained on millions of prior solar events. Within 1 second, a prediction is generated. Within another second, signals are dispatched globally. Power grids begin isolating vulnerable nodes. Airlines reroute polar flights. Astronauts aboard the ISS retreat to shielded modules. Banking systems pause high-risk transactions. No human intervention required. Just decision-making at the speed of light, because the threat is moving just as fast. This approach mimics severe weather alert systems on Earth. Just like sirens warn towns of incoming tornadoes, solar sirens would act as an early warning system for space weather emergencies. Governments, businesses, and even households could receive push notifications in real time, advising them to prepare, power down, or wait. Such systems are already being tested. In addition to Dagger, other models like Enlil, WSA Enlil plus Cone, and Solar Sentinel are providing simulated storm trajectories and strength forecasts. The European Space Agency, ESA, is working on its own warning network, and Japan, India, and China are also developing domestic space weather forecasting capabilities. But perhaps the most groundbreaking idea is one still on the drawing board: embedding sensors into Earth's infrastructure itself. This vision includes smart power grids equipped with embedded solar flux detectors, deep-sea internet repeaters that can self-regulate when storms are incoming, and even AI-managed aviation systems that adjust altitude or timing to minimize radiation exposure during a storm. At Infinity Beyond, we know this sounds futuristic, but it's already being quietly implemented behind the scenes. Just as meteorology evolved from barometers to Doppler radar, space weather prediction is now evolving into real-time, AI-driven defense. In our next segment, we'll return to Earth's surface, specifically to the vulnerable power grid. We'll explore how a Carrington-level event would cripple not just the lights in our homes, but the entire backbone of the modern economy, plunging civilization into darkness. Because when the sun roars, the only thing between us and silence might be a siren. Transformers, the unsung heroes of our electrical systems, are responsible for regulating and transferring power across vast distances, from massive power plants to your laptop charger. But they also represent one of the most vulnerable links in our technological chain when it comes to solar storms. At Infinity Beyond, we delve into the terrifying possibility that a single solar event could cripple civilization's entire electrical backbone, starting with the very devices that keep the lights on. Here's how it works. During a geomagnetic storm, Earth's magnetic field gets compressed and twisted by the incoming burst of charged particles from a coronal mass ejection, CME. This distortion induces electric currents into conductive materials across the ground, including power lines that stretch for hundreds of kilometers. These currents, called geomagnetically induced currents, GICs, flood into the power grid and accumulate inside transformers. The result? Excessive heat buildup. Magnetic core saturation. Insulation breakdown. Meltdowns and explosions. Unlike small-scale electrical surges that trip your home's circuit breaker, GICs can overwhelm the core design of massive industrial transformers. When they fail, the damage is catastrophic. And worst of all, these transformers are not easy to replace. Each one can cost millions of dollars, take up to 2 years to manufacture, and often needs to be custom-built for specific infrastructure. And here lies the real danger. There are no global stockpiles of spare transformers. No backups, no immediate replacements. Just a slow, grinding path to recovery. According to a report from the National Academy of Sciences, a Carrington-level solar storm could destroy up to 350 large transformers in the U.S. alone, potentially leaving 130 million people without power for months or even years. Water systems would shut down. Hospitals would rely on limited backup power. Food supply chains would collapse. Emergency services would falter. Chaos would fill the void. In 2012, experts estimated the economic cost of such a disaster in the U.S. at $2.6 trillion, with a 10-year recovery timeline. And that's just one country. Globally, the interconnected nature of power grids means that a large-scale failure in one region could cascade into others, especially across Europe and Asia, where cross-border power sharing is common. A transformer meltdown in Canada, for instance, could cause flickering and blackouts as far as Texas. To counteract this threat, some nations have started to invest in resilient transformer designs, automatic load-shedding systems, and grid-level circuit breakers that can redirect excess current. But progress is uneven. Many developing countries, especially those near the magnetic poles, are ill-prepared. At Infinity Beyond, we believe the time for reactive thinking has passed. We must shift to proactive resilience. In our next segment, we'll examine how a global blackout triggered by solar activity would impact the internet, banking, communications, and even public safety. Because in the 21st century, losing power doesn't just mean darkness. It means disconnecting from the world. Because if the heart of the grid fails, everything else flatlines with it. Is this nihilistic? Perhaps. But at Infinity Beyond, we believe it's also beautiful. The universe has written its own epic, from the quantum tremble of the Big Bang to the dying light of the last star. We are part of that story, a brief but dazzling spark in the long cosmic night. To be alive now, in a time where the sun still shines, where stars still sing, and where thoughts like these are even possible, is a privilege beyond comprehension. In our next segment, we'll answer the ultimate question: is this truly the end? Or could there be a rebirth, a new universe, a new Big Bang, a new beginning? Because as one cosmos fades, another may already be stirring in the dark. Could there be another universe after this one dies? It's one of the most profound questions ever asked, and perhaps one of the most hopeful. At Infinity Beyond, we explore what science, philosophy, and cosmology suggest. Maybe the end isn't truly the end. Maybe our universe is just one chapter in a much grander story, a story of death, rebirth, and eternal cycles. One of the most ancient and now scientifically reconsidered ideas is the cyclical universe, a cosmos that expands, collapses, and is born again in an infinite loop. In this theory, after the universe reaches its maximum entropy, when even black holes have evaporated, quantum fluctuations could spark a new Big Bang, creating a fresh cosmos with new laws, particles, and dimensions. A reset, a rebirth, a cosmic phoenix rising from its own ashes. Modern physics entertains this through models like the Big Bounce conformal cyclic cosmology, championed by Sir Roger Penrose, ekpyrotic universe, arising from brane collisions in string theory. Each offers a version of a reality where our universe is not alone, and time may be circular, not linear. There's another possibility. Our universe is one of many in a vast multiverse. Quantum theory, cosmic inflation, and string theory all suggest that there could be countless other universes, each with different physical constants, dimensions, or timelines. Some may be lifeless. Some may birth stars unlike ours. Some may even host civilizations wondering, just like we are, if they're alone. In this view, even if our universe dies, the multiverse lives on, an infinite canvas where creation never ends. At first glance, the thought of our universe ending might feel terrifying. But in the grander context, it becomes a moment of transformation. We are part of a cosmos that is not static but restless, evolving and alive, even in its death throes. And perhaps, just perhaps, the atoms that make up our bodies will one day become seeds in another universe. What if the gravity that pulls our galaxies apart is also the mechanism that births the next one? We began as stardust. We became conscious. We looked back at the stars, and now we ask, what's beyond the end? At infinity, beyond, we don't offer certainty. We offer the one thing more powerful, curiosity. In the next segment, we will explore the human meaning behind all of this. What does it mean to be aware, fragile, temporary, but able to understand the cosmos? Because in the end, the story of the universe is not just out there. It's inside us, too. What does all of this mean for us, as humans? We are tiny beings living on a pale blue dot, circling an average star in a quiet corner of a vast galaxy. And yet, we can ask about the death of stars, the birth of universes, and the nature of time itself. At Infinity Beyond, we believe this ability isn't just impressive. It's sacred. The fact that the universe evolved in such a way that particles, atoms, and molecules could eventually form living beings who then looked back and understood the cosmos, that is extraordinary. Our brains, shaped by evolution, are patterns of stardust that learn to think. We are made from the same carbon that once burned in dying stars, and we carry in us a history 13.8 billion years in the making. The universe created us, and now, through us, it knows itself. In the face of cosmic scales, trillions of years, infinite space, it's easy to feel insignificant. But we argue the opposite. Precisely because our time is brief, our choices matter more. We are a civilization alive during a rare and golden age. Stars still shine. Life still blooms. Discovery still continues. We must use this moment to cherish our planet, protect our and expand our knowledge, not for ego, but for the deep responsibility we have as the universe becoming aware. Maybe, in the distant future, someone or something will find traces of our time. A spacecraft drifting, a signal caught in deep time, a fossil on a frozen world. What will it say? That we looked up, that we wondered, that we tried. Maybe our story isn't just for us. Maybe it's for the next spark of life, in the next universe, trying to understand where it came from. We are not eternal, but the thoughts we think, the art we create, the love we give, they echo far beyond our short lives. Even as stars fade, meaning remains. Even as the universe grows cold, curiosity burns bright. At infinity beyond, this is the message we carry. You are small, yes, but you are part of something infinite, and that makes you magnificent. To whoever may hear this, from wherever or whenever you are, this is infinity beyond, and this is our message. We are a species that once crawled from the ocean, stood upright, and gazed at the stars. We built tools, cities, telescopes, and dreams. We split atoms and mapped galaxies. We searched for meaning in the deepest dark and found light. We lived on a fragile rock, warmed by a yellow star, and we called it home. And even though we knew our place in the cosmos was small, we dared to ask the biggest questions. We didn't just watch the stars, we told stories about them. We turned hydrogen into hope, gravity into guidance, distance into destiny. We explored not because we were lost, but because we were curious. And in that curiosity, we found our humanity. If this recording survives, if some distant intelligence, machine, or future human finds these thoughts, know this: we existed, we wondered, we reached, we fell in love with the universe, with each other, with the mystery of it all. And even in the shadow of extinction, we chose to create. We turned knowledge into legacy. We turned fear into fuel. We turned time into testament. This isn't goodbye, it's an echo, a whisper from one moment of consciousness to another. May you too look up. May you wonder. May you remember us, not for our wars or our fall, but because we were one small voice in the dark that chose to speak. This is infinity beyond, and this is the end of one journey, but the beginning of countless more. Stay curious, stay human, stay infinite.